just like we can have variables on one side whenever we have exponents, we can have the same thing for these. So in order to be able to solve equations that have variables on one side, we need to remember a little trick that we learned. And that is, if we have an exponent base and a log base that are equal, then the exponent base and log base cancel out, and we are simply left with whatever the log was being taken of. So we had log base 3 of x, so it simply leaves us with x because the exponent base 3 and log base 3 cancel. Same thing happens with natural base and natural log. It will equal x. And in addition, common base, remember that that's a log, an exponent base 10 and a log base 10 or common log. These will cancel and simply leave me with an x. That's some of the exponent properties that we learned last time. All right, so in order to be able to solve something that has a log only on one side and variables on one side, we are going to do what's called exponentiating both sides. In other words, we are going to make an exponent out of both sides. And if we're going to make an exponent out of both sides, we want to use an exponent base that's convenient for us, that's going to do us some good. So the exponent base that we would select for this one, well, I have a log base 3, so let's make an exponent base 3, and I'm going to make this entire thing an exponent with a base of 3. So in fact, instead of rewriting the whole thing, I'm just going to write a gigantic 3 here. And so this is 3 raised to the log base 3 of x plus 4. But if I do that to one side, I have to do this to the other side too. So I'm going to have a gigantic 3. That's my exponent base. I have 3 raised to the second power. Well, I know what 3 raised to the second power is. 3 squared is simply 9. On this other side, remember that the whole reason for exponentiating, I know that's a big word, making it an exponent, is that the base of 3 on the exponent and the log with the base of 3 will cancel, and I am simply left with whatever was in the exponent. It kind of falls out. X plus 4. Now I have a really simple algebra equation. I can just subtract 4 from both sides and get a final answer of x is equal to 5. Now, there is one other thing that we have to do here when we are checking logs and solving them. We need to remember that the log parent function has a domain that only starts at 0. Remember that it had a asymptote at a value of x equals 0. And so the basic log function was not defined. It had no x values if we tried to plug in a negative number and take the log of a negative number. And so we need to keep that in mind. And so what we want to do is just double check that whatever we are taking the log of is not a negative number. And so let's plug in the 5 that we came up with for x and just make sure that what we get that we're taking the log of is not a negative number. So this is our little check. And we can get those extraneous solutions sometimes, because if we get a number less than 0 when we check what we're taking the log of, then it's extraneous and it doesn't actually work. In fact, if you tried to do it in your calculator, you would get an error. So we want to say that x plus 4, the thing we're taking the log of in our original equation, has to be bigger than 0. Remember, not equal to 0 because we have an asymptote exactly at 0. Well, our x is 5. 5 plus 4 greater than 0. Well, yes, 9 is greater than 0. That's good. So we can, in fact, say that x is truly equal to 5. So actually, I suggest that you don't even box this until you know that your check works out. Let's look at another one of these. Pause the video for a second and think about what exponent base we would use in order to get rid of a log with a base of 2. Then come back here and let's go ahead and finish the problem out. All right, well, hopefully you said that in order to cancel out a log base 2, we needed an exponent with a base of 2. So I'm going to write a great big old base here of 2, and now this whole thing is an exponent with a base of 2. But if I do that to one side, I also have to do it to the other side. So the right side is 2 raised to the third power. 2 raised to the third power, well, that's pretty easy. That's just an 8. And now that I have an exponent base 2 and a log base 2, those will cancel once again, and I'm left with 5x minus 17 is equal to 8. I want to add 17 to both sides to continue solving. 5x is equal to 25, and dividing by 5, I get that x equals 5. Now this time, I'm not even going to box that until I double check it and make sure that it works. So come over here to the side and do your check. And the check is, we want to make sure the thing in parentheses that we are taking the log of isn't less than 0. We want it to be greater than 0. So 5x minus 17 needs to be greater than 0. Well, I know that x is 5. So 5 times 5 minus 17 greater than 0. Well, that's an 8, and 8 is, in fact, greater than 0. So I can say that x equals 5 is a valid solution and not extraneous.